continue, I want to discuss resonance structures. Okay, this is something you're going to see much more in organic chemistry if you take it, but it's something that's sort of interesting that happens. Okay, so sometimes you have compounds that have multiple acceptable and equivalent structures. Okay, and that obviously, if you do the formal charges on them, is going to be the same for all of them. So let's look at ozone. Let's do ozone. So let's do let's do it by hand. Let's do ozone by hand. So I have O3. Okay, so step one would be to get the total number of valence electrons. So total number of valence electrons. Well, I have 6 for each carbon, each oxygen. So I have 18 electrons. Cool. Now, I need to identify my central atom. Well, no dur, it's going to be oxygen. Shocker. And now I'm going to have to try to put 18. I'm going to try to distribute from the 18, 8 on the wings. So each one on the wings on the periphery is going to get 8. So 1, 2, 3, 4, 5, 6, 7, 8. Okay, so I have 16. And then the step number 3 is to put whatever is remaining on the central. So this is remaining and it's on the central. All right. So now this has 8, he's happy. This has 8, he's happy. This has 6. See that? This has 6. He's not happy. He wants more. He's greedy. So how would we do that? We just need to share some more. So I'm going to do is I'm going to move this over here, and I will do this. Now look, this has 8. Now we're going to have to. I'm going to redraw that again. Don't worry. This has 8. This has 8. This has 8. They're all happy. So I have this structure. Okay. Now, how do I know, honestly, that the double bond is not here? I can also draw it so that it's like this. Which one's right? And this is where resonance comes in. So I mean, I can omit these if I want to. So these look equivalent, but they're not. I mean, these are three separate atoms. So I can't just say, well, between 1 and 2 is always going to be double, and between 2 and 3 is going to be single. It doesn't work like that. Nature doesn't work like that. You can't just distinguish 2 oxygens. They're all the same. Otherwise, we would have a different identity for each oxygen. So I have this and this. Which one is correct? What do we do? So the answer is kind of both and kind of neither. And this is where resonance comes in. And so what we say is that it kind of looks like an amalgamation of both. Okay, so ozone structure is somewhere in the middle, and it will look sort of like, well, let me draw it for you. The way we draw it in chemistry, you could draw it like this. So it would look like this. Like this, okay? So not quite a double bond, but I want to show you here that these 2 bonds are identical to these 2 bonds. There is no distinguishing between them. So actually, you should have 4 dots. These are exactly identical. There's no separation between them. So I can also draw it like this. Chemists also draw it like this to denote that they're both equivalent. So it may kind of go back and forth a whole bunch of times. Or you could say like these pairs of electrons kind of like move around here, and they have like a little water park, and they kind of walk back and forth, so everyone's happy. And so this is what we call resonance, or resonance structures. And you see that quite a bit. And to show you, the bond length of ozone is larger than the bond length of a double bond, and it's smaller than that of a single bond. See, somewhere in the middle. So it goes to show you that this thing I drew here is sort of like 1.5 bond. That is not a thing, but think about it like that. It's like sort of like 1.5 bond. Okay, that's a resonance structure. Okay, and we see that not just in ozone, we see that here in the carbonate ion. If you were to do the Lewis dot diagram for the carbonate ion, and I encourage you to do that as practice, and here's the answer, you would see that you have one double bond here. And so for you to say that this oxygen is special and these other ones aren't is nonsense. So it has to kind of walk around a whole bunch. Actually, let's do this example because I promised you to show you what happens when you have a negative ion. So if I have a CO2 minus 2, right, so carbonate ion, CO3 minus 2, sorry. CO3 minus 2, okay? I need to get the total number of valence electrons. Total valence electrons. So carbon's going to give me 4. Oxygen, there's 3 of them. Each one's going to give me 6. And there's 2 more from this. This gives me 2. That's that thing that we never used before. This is it. So this one gets 2. Great. Now, I'm going to add them all up. 4 plus 18 plus 2, that's 24. Okay. And I'm going to do, again, carbon is going to be the one in the middle, usually. 24. I'm going to give 8 to each one of these. And you could see right here, 8, 8, 8, 6. He's unhappy. So what I'll do is I will move this over and share it. Now, carbon has 8. Oxygen is 8. Everyone's 8. Everyone's happy. But what I'm getting is, and this has to be denoted as a negative 2, by the way. So I get this as my bond structure, like this, my structural formula. But then again, I can't just describe this to be the coolest oxygen around. They are all equivalent. So what you actually do is you show that it's resonance structure. And they kind of go back and forth. And this is like 1 1/3 bond, if you will. So all 3 are equivalent. It happens in benzene too. Benzene looks like this. And it alternates double, single, double, single, double, single. But then why wouldn't it alternate single, double, single, double, single, double? And so it does. And so we write it like this. And organic chemists actually write it like this, just so you know. So I just showed you what it looks like this. And we say that it's equivalent with this, right? That's what we were saying. Okay, and what organic chemists do very often, because benzene shows up quite a lot in organic chemistry, is they write it like this. This is the resonance structure for benzene. This circle just means they're circling around, all doing their thing. Okay, like that water park thing I was telling you about. They're all just sliding around. All right, so that's resonance structure. Now I want to talk about exceptions to the octet rule, and we will see them when we do the next unit after in a bit. This happens quite a lot. And so some atoms sometimes only need 6, and I will tell you that boron and beryllium are the ones that's going to happen. And so you won't see this very often in chemistry, and even in our assessment. I probably won't give you too many of these because it's not fair. The octet rule is the one that reigns supreme. So as central atoms, boron and beryllium sometimes, not always, need 6. So you would see these things, okay? And sometimes some atoms, especially molecular compounds, you would get more than octet. This happens quite a lot with phosphorus, with sulfur, and with noble gases. So I'm just showing you some examples where this happens, and it's kind of weird. And I promise I'll show you examples when we talk about the next unit, the one after this video. All right. I want to talk one more thing about electronegativity. So we talked about trends in the periodic table. This is one thing that we didn't discuss, but it's very similar to what we've seen already. Electronegativity is how much an atom wants to steal another's valence electrons. Okay, fluorine is the best quote-unquote thief, and cesium and francium are the ones that want to give it up the most. They have a very, very low electronegativity. So when say lithium and fluorine get together, all right, fluorine will take away lithium's electron. When fluorine and oxygen get together, it won't. It will form a covalent bond. And so what we do is we actually subtract the two numbers to determine whether we get covalent bonds or ionic bonds. Okay. And so the difference between the two, basically it's a general rule, and you take the absolute value, so you don't have to worry about, is it 1 minus 4 or 4 minus 1? Doesn't matter, just make it positive. So let's look at NH3. N is 3, H is 2.1, and we get 0.9. So it's covalent, right? So anything below 2 is covalent, anything larger than 2 is ionic. It's not, it's just a heuristic. Carbon dioxide, 3.5 minus 2.5, it's 1, it's covalent. Sodium chloride, sodium here is 0.9, and chlorine is 3. I subtract them, make it positive. 2.1, that's ionic. Magnesium oxide, 1.2 and 3.5. I subtract them as 2.3. Notice that when I'm doing this, I don't do 2 times oxygen. I just go C minus O, N minus H, Na minus Cl, Mg minus O. That's what I do, okay? So this is just a hard and fast rule. It's not always going to work, but it gives you a pretty good approximation. Just want to mention it. Okay.